Hi everyone. In today's session, we will be doing the post processing. Last time, when we did the post processing, we imported all the meshes, contours, and scenes and vectors. In today's session, we will actually try to create those contour plots ourselves. So, according to the tutorial manual, for the plots should have all the plots corresponds to a voltage of zero point 0.5 volt and a current rating of 17.2 amperes. So how can we check it if our model is currently at the same at the same at the same parameters? So we can check this by using the report definitions. In the report definitions, we can check for the cell voltage. If you go to the cell voltage and compute it, see this is at 0 0.5 volts. And to check the current, we will check the current at the voltage tab, but because this is operational, the current at the current tab and the voltage tab wouldn't be that different. So we'll go to the voltage tab and compute it. So we get a voltage of 17.2 amperes. If you were to check for the current tab, it will be very slightly different. See, there is a very slight difference, not much. So but voltage tab is the correct region from where we should take the current reading. Now in order to get the contours, we'll start from the contour plot. So the first contour plot that is given in figure 30, that is the temperature distribution in anode and cathode. So we'll go to contour and start making a new contour plot. So we'll go to new contour and we can say temperature distribution and this is static temperature. And the fluid, we can directly use a 3D fluid, or we will have to select all the surfaces which corresponds which cover all the domain or this. So we'll just select all the fluid regions, but we don't want the flow channels, and we want the solids and display. Now last time we set outer face cullings to so how can we, okay, if we go to the view options and uncheck the outer face cullings, apply, close. Now you can see there we got very good distribution for the anode, cathode and the current collectors, but we can uncheck the global range. Now this is pretty much the same as shown in the tutorial, and this we can actually double click it and make it float types. So now this is a very good contour plot for showing the temperature distribution in the anode, cathode and the current collectors. In order to get a picture for publication purposes, we can go to the save picture tool and save it like JPEG, and if you preview it, you'll get a very nice background picture. So we can save it as temperature distribution. This is our session 3, and we'll save it as temperature distribution. So if we save it like this, and in our folder we'll get this picture saved, close. So this is the first contour plot that is given in the tutorial manual. The next is the temperature, but anode and cathode, more importantly we need the temperature distribution at the electrolyte. So the next control plot will be a temperature distribution at the electrolyte. So we'll call it temperature electrolyte. So now this is static temperature at the electrolyte surface. So make sure we select the correct surface. That should be wall, electrolyte, anode or cathode. That should give the same temperature. So this is the same. Now we get the same distribution as shown in the tutorial, but if we go to float, but we still need to add the outer box bounding. Like in the tutorial we can see an outer geometry which is where transparent. So in order to do that we need to go to draw mesh. Once we draw the mesh and select outline, it will select all the surfaces, but now we should select which surfaces we don't need. Okay, so first display. Okay, these are the surfaces that it will display. And we can add the transparency to 85%. So the faces which we don't want to display, we only want the surfaces of the flow channels, not the walls of the flow channels. Yes, one of this is this surface. Don't want this. And for the colors we can have it by type now. This is getting green, so I think probably there's a that is better. Okay, we can even increase the transparency more up to 90%. Yes, this is better. So now if we show, now it makes pretty better, it makes a better picture about the anode and cathode. And we can add the, if we add the inlet and outlet to the mesh, so if we add the inlets and outlet, it will give the arrows also, but we only need it the inside of it, so we can have the anode side unchecked. So this will give us the fuel flow. Yes. So with this we can now have a better idea or the more visual better illustration of the electrolyte distribution within the fuel cell. Okay, the next distribution is the current interface current density. So we'll again go to the control plot and with the same distributions, or we can just copy it, copy electrolyte distribution, copy it. And this is not the temperature, this is current density. And this is actually uses defined memory. Interface current density. You see the interface current density, it is almost the same as given in the tutorial manual, but we'll again draw the mesh and exclude the inlets and outlets. Display. It's too light. So we get the distribution of the interface current density. Now we will add one more thing to it. We normally we want, like, if this is this direction, we take a picture in this direction and we display it, that's okay. But then we again go back to the temperature distribution at the electrolyte and display it. Now it is showing the same scene, but we can have another better representation way by adjusting the our geometry in the required position, and after displaying it in the required position, then we can have it use active and we will save a state to it. So the next time, even if we change it and go to the temperature distribution and display it, now it will display the temperature distribution in the same orientation. But if we go to state 0 now, you see we get the same distribution in the same state. And likewise, if we change the orientation to any other orientation and go back to the current density and select state 0, display. I see this is much better approach to saving a state, because when we have multiple contour plots, we want the same orientation of our geometry. So our next is the Nernst potential. So we close this and add a new contour for the Nernst potential, and that is again at the electrolyte interface. Now the Nernst potential at the cathode side and the anode side will be different. So this is the Nernst potential at the cathode side, and if we give it float, so you can see the Nernst potential is giving mostly red regions. But if you go to the anode side and display it, range, global range, so this is how they have done by setting the range or clipping the range. As you can see in the tutorial manual, they have clipped the range at 0.75. This gives a better distribution of the Nernst potential scatter on the electrolyte interface. So the next is the activation over potential distribution at the electrolyte. Again, we will go to the contours, new contour plot, and here we will select the activation over potential. All these are from user defined memories and activation over potential. Now the activation over potential will be different for the anode side and the cathode side. So first we will select the cathode, change it to float. So these are the voltage drops that are recorded. Again, we can have a clipping section instead of global range. Okay, and normal auto range works perfectly. Sometimes we need to clip the ranges according to our desired criteria. So anode, they will be slightly different for the anode and cathode. Now now the most important is the voltage distribution. The final voltage that we get is, so we have a new contour for voltage distribution. Give it voltage, and this is not in user defined memory, it is actually a user defined scalar. So the electric potential is a scalar value, not the, we can have the global range also, and it is important to note that we have getting a maximum electric potential of 0.57 while our actual operating voltage is only 0.45 volt. Make pl- please see that this is actually at the electrolyte. This distribution is shown at the electrolyte and not not at the output voltage tabs. So at the output voltage tabs you get 0.5 volt difference, but at the electrolyte it has to compensate for all the losses, activation over potentials, concentration losses and resistive losses. So the net the output voltage that we get is 0.5 volt. And now again we need to have a clip section, so we can clip it, not the auto range or global range. So the maximum we can go to 0.57 with minimum of 0.5 and then display. Now you get a much better distribution to see the insights that which positions actually produce the maximum voltage. And if you go to the anode side, I said that it doesn't produce that much voltage. So if we go to the auto range, you'll see that it's actually not producing any voltage at all, only over here slightly, which is due to the losses or the gas crossovers. So the voltage is actually being obtained at the cathode side. Now the next is the volumetric distribution of the electric potential. So we'll have another contour plot, new voltage at cathode surfaces. This is user defined scalar electric potential. We'll auto range it for the this, and let's let with cathode. We would like to add the current collector also, so it is from the cathode current collector. Now get the same distribution as shown in the tutorial manual. You can adjust it, and make another state. Okay, so now this is the voltage at the cathode surfaces. Again, we should have it in float. Like this, we can have all the molar distributions at the electrolyte. This is very important to get the molar distributions at the electrolyte in order to check if there is any local starvation for hydrogen or oxygen. So we can go to contours and select new. Again, at the hydrogen will correspond towards the anode side and the oxygen will correspond towards the cathode side. So we go for mole fractions of H2. For hydrogen mole fraction, we definitely need to go towards the anode side of the electrolyte. So we'll select the vol electrolyte anode and species concentration mole fraction of H2. Save display and we'll select it state 1, no, state 0. Okay, and again float. We can draw the mesh also. Now this is the distribution of hydrogen available at the electrolyte interface from the anode, but if you go towards the cathode, obviously it's going to be 0. You see, it's 0 because the hydrogen never goes towards the cathode. It's not present at the cathode, it's always present at the anode. Now the same we will do for the mole fraction of oxygen. Save it new. Mole fraction of O2, species, mole fraction of O2, and now we will select so this is the distribution of oxygen at the electrolyte interface. From the cathode side, we can draw the mesh again. By this, we can have all the contour plots that are required for our study that are of our concern. One important thing is that we want to see the volumetric distribution of oxygen in the cathode. So for that we can also have a contour plot, a volumetric contour plot. So we can go to contour plots, new, oxygen distribution, now global range, and we'll select the fluid cathode. This is better demonstrated in, so at the inside, at the internal is the oxygen and it diffuses slowly towards the electrolyte surface. As you can see, it is decreasing as we are going towards the electrolyte interface. The oxygen concentration is decreasing. You can draw the mesh also. The next very important plot is the vector plot for the electric potential. So for that we will go towards the vector plots, go to new, vector plots. This is electric vector plots for the current density, and this is colored by current density or electric potential. Okay, so we should draw the mesh. It's giving too many. Now you see we can get the electric potential vector plots for the electric potential. This is very similar to that given in the tutorial manual. So the electric potential and the distribution of the electric potential and at every cross section of our fuel cell. With this we can conclude this demonstration for getting the post-processing results, which help in much better visual inspection or visually understanding of the problem. Thank you, and we will see next time. Thank you. Bye.